Nowadays, more and more people trust science and its achievements. Consider the recent year, which was rocked by the spread of COVID-19. The entire globe is basing its decisions on what scientists are discovering. If we go back in time, the situation was completely different. Science was not as sophisticated as it is today, and people did not always believe what professionals said, as the Greek belief in fate. The transition between these two opposing perspectives on life occurred in the 18th and 19th centuries, during the periods of Illuminism and determinism. Although this revolution in human beliefs and habits has undoubtedly resulted in significant technological advancement that continues to this day, many of the conclusions reached during that time period are completely incorrect. Trusting the scientific method is a good thing to do, but putting all our hopes in science and believing that everything can be predetermined by mathematical equations is illogical reasoning. Indeed, certain significant discoveries made at the turn of the century revealed a hidden and completely paradoxical behavior of nature. I'm talking about quantum mechanics, specifically the Heisenberg Uncertainty Principle, a surprising conclusion that has radically transformed our way of thinking about almost everything in our universe. The entire 20th century was affected by this finding, which completely undermined our previous deterministic view of science. The quantum mechanics revolution has affected hundreds of poets and writers. But what exactly is it about? Who was Werner Heisenberg? What is his guiding principle? And why did it have such far-reaching implications in fields as diverse as literature and philosophy? These are the topics of this video, so if you're interested, stick with me and prepare for an exciting voyage through quantum mechanics. The Heisenberg principle is one of the most important in physics, and it must not be violated in any experiment. In a nutshell, it argues that it is not possible to measure a particle's position and momentum with infinite precision. The product of the mistakes in measuring these two quantities must be greater than a constant amount. As a result, if you know where a particle is, you disregard its velocity, and vice versa. Unfortunately, as you might expect, understanding why this principle works is not that simple, so we'll start by looking at what physicists thought before the development of quantum mechanics. Given these foundations, we'll go over the uncertainty principle and try to figure out why it contradicts previous theories. What was it like to study physics before the 20th century? Many things can be said, but to begin our description, we must begin with Newton. Sir Isaac Newton, known as one of the 3 or 4 most brilliant scientists of all time, established what is known as classical mechanics, along with other important research on optics and, of course, gravity. What are the main ideas behind this theory? The first is the law of inertia, which states that if a body is at rest or moving at a constant speed in a straight line, it will remain at rest or continue to move in a straight line at constant speed unless acted upon by a force. Galileo Galilei developed the law of inertia for horizontal motion on Earth, which René Descartes later expanded. The second is undoubtedly the most famous physics equation, and it states that the force acting on an item is proportional to its acceleration multiplied by the mass of the object, F equals ma. The third is not applicable in this situation, but it is always important to remember, if an item A exerts a force on an object B must exert an equal magnitude and opposite direction force back on object A. Newton and his successors also made significant contributions to the development of mathematical calculus. Derivatives and integrals are inextricably related to classical mechanics. Even if we don't go into detail, it's important to note that mathematical methods may be used to calculate the velocity and position of a moving body based on its acceleration. What is the end result of all I've said? If we can determine the mass of an item and the force applied to it, we can extract the acceleration using Newton's second law, and maths will provide us with its velocity and position as time passes. This is a completely deterministic model. In truth, Newton's findings regarding physics were the driving force for Illuminism. However, physicists of the time recognized that many occurrences were not explainable by this classical theory, but when big discoveries in electricity and magnetism were produced in the 19th century, the concept that science could decide everything skyrocketed. Indeed, physicists such as Maxwell and Faraday recognized that electricity and magnetism were two sides of the same coin, and they developed the electromagnetic theory, which established the existence of electromagnetic waves. Furthermore, all earlier optics research was simply a result of the four Maxwell equations that governed electromagnetism, because light was simply a sort of electromagnetic wave. What was the end result of all of this? Almost every phenomenon on Earth can be explained completely by gravity, classical physics, or electromagnetism. It was the pinnacle of determinism. As a result, physicists in the 20th century realized that in order to explain the behavior of atoms, they needed to entirely rethink their way of thinking about the world, abandoning determinism. Classical theories were unable to explain why humans exist since they anticipated that the medium life of an atom was only a fraction of a second, completely inaccurate. To better characterize a specific phenomenon known as the photoelectric effect, Einstein argued in 1904 that light is quantized in little packets of energy known as photons, and that in some situations waves can be considered as particles with discrete energy values. More specifically, each photon has an energy proportionate to its time frequency due to a constant known as Planck's constant. Following that, the great Louis de Broglie attempted to flip this association in 1924. He claimed that all particles may also be viewed as waves with a wavelength equal to Planck's constant divided by momentum, which is the product of mass and velocity. As a result, the shorter the wavelength, the greater the particle's momentum. When discussing waves, we must also discuss Fourier transforms. Who created this sophisticated mathematical tool? It was developed by Jean-Baptiste Joseph Fourier, a French mathematician. After fighting in the French Revolution, he attended the École de Paris and listened to outstanding lecturers such as Pierre-Simon Laplace and Joseph-Louis Lagrange. But wait, what exactly is a Fourier transform? Don't worry, we won't get too deep into the mathematical tools employed in this area. Instead, we'll just try to get a sense of what it is. The Fourier transform of a light wave is the distribution of its temporal frequency components. All functions, according to the principle, can be recreated by a continuous infinite sum of waves of varying frequencies. The Fourier transform determines the weight of each frequency component. A solar beam, for example, will have a peak on orange frequencies and declining values for other hues. Similarly, the Fourier transform of a particle wave will produce a spatial frequency distribution that is proportional to momentum due to de Broglie's hypothesis. As a result, the Fourier transform might shift our perspective on the particle from position to momentum. Even though we will not discuss the mathematical expression of this topic, we must highlight its most essential aspects. If the function used to calculate the transform is defined on every conceivable point, the Fourier transform will be limited to a discrete set of frequencies. If the function is limited in one region and zero in another, its transform will be continuous, and the function will be composed of an infinite number of frequencies. Consider a perfect yellow light ray that goes from minus infinite to plus infinite. He will be formed solely of a spike on a single frequency corresponding to the yellow color, followed by a discrete Fourier transform. But what if our light ray only exists in one place and is zero elsewhere? The transformed will always have a peak on the yellow frequency, but it must also be composed of other waves that can zero the amplitude in all other areas of space, so that the transformed is continuous. The same principles apply to a wave particle, such as those proposed by de Broglie. The narrower the spatial distribution of the function to be transformed, the wider the distribution of momentum. Are you getting these ideas? We're almost there, with the Heisenberg Uncertainty Principle formulated in, but to have a clear intuitive understanding of why it works, we need to introduce one more thing: root mean square error. But what exactly is it? In practice, it refers to the uncertainty in measuring a physical quantity. For instance, if the root mean square error is really low, our precision will be very high. To put it simply, if a Fourier transform expressing momentum is wider, the error in its value will be larger. Physicists typically spend their entire careers developing appropriate technologies to eliminate this error in order to achieve better outcomes in their investigations. Hundreds of volumes have been written on the subject, but in quantum mechanics, it is not possible to utilize methods to reduce error. There is an inferior limit beyond which we cannot proceed. But why? Because if we measure a particle's properties and deal with its waves to make a narrower spatial distribution, the relative momentum distribution, i.e. the Fourier transform, will grow wider and vice versa. This is the essence of Heisenberg's uncertainty principle, one of the most fundamental postulates of quantum mechanics. We obtained it from wavy considerations that were not rigorous, but its correct formulation derives from more complex mathematical ideas that we will not investigate. To be more specific, the product of the uncertainty in the position and the momentum must be greater than half the reduced Planck constant, which is the Planck constant divided twice pi. As a result, if we try to minimize the root mean square of position to zero in order to comprehend where the particle is, the uncertainty on momentum grows rapidly to infinity, and vice versa. This outcome is both extraordinary and horrifying. It's a completely different way of thinking about physics. Nature, which may be thought of as made up of quantum particles and waves, forbids us from measuring everything with infinite precision. We can't calculate a particle's exact trajectory. We must limit ourselves to saying that there is a certain likelihood of finding an object in a region. Newtonian determinism has died. Yes, science is extremely powerful, but it is science that has discovered that not everything can be predicted using math and that we can only limit ourselves to calculating probabilities, something we can certainly manipulate well, but also something that is not so far removed from the Greek fate we discussed earlier. Do you find quantum mechanics fascinating? Did you already know about Heisenberg's uncertainty principle? Would you like to learn more about wave-particle duality? Let us know in the comment, and don't forget to like, share, and subscribe.